We're now ready to talk about a new type of classifier. And actually, we're going to talk about two classifiers. As promised, we want to start getting some more machinery to deal with more complex classification problems, which means we have to get out of this linear classification, least squares, logistic regression, and linear discriminant analysis, and get into some nonlinearities. We're going to introduce support vector machines. And there are two basic types of support vector machines: linear, which I think you already know what that means, and nonlinear. To get to the nonlinear, we've got to start with the linear. So we'll start there, and we'll make our way to make sure we understand how support vector machines work, and then we'll get to nonlinear classifiers. Just to foreshadow a little bit, it's going to be the same game. We have a classification problem. We have some features that we extract. We have a labeled data set. We define an objective function, and we optimize that objective function. Support vector machines just have a different objective function and a different optimization, and then nonlinear support vector machines are a generalization of the linear support vector machines. So let's get started. Let me remind you that with the linear discriminant analysis, we selected an objective function. The objective function was to minimize the within-class variance and maximize the across-class variance to determine a linear subspace onto which we could project the data and then do classification. Okay. Support vector machines, linear support vector machines, going to play the same game, but we're going to optimize something a little bit differently. In particular, we are going to maximize what is called the margin, or the separation between the two data sets along a linearly separable space. So I misspoke early on. I said that there's two types of support vector machines: linear and nonlinear. Within linear, there are two subcategories. One is called the linearly separable, and one is called the non-separable. We'll talk about those, of course, as well. Let's start here in this case where you have this very nice clean data set where one set of data are linearly separable from another class in the red and in the blue. And now, instead of within class variance, across class variance, we just have a different objective function. Is it better or is it worse? Neither. It's just different. And so let's talk about that and then how we build these classifiers from linear to nonlinear. So I'm going to define the margin, quantify it for us in a little bit. But right now, think about this. The data is linearly separable by assumption. And the margin is take the point in one class that is closest to that separating dotted line, and take another point that is closest and draw those two solid lines that you see here. What we would like to maximize for the linearly separable support vector machine, SVM, is the width of that margin. Sure, that makes perfectly good sense. Take the blue point that is closest to the separator, take the red point that is closest to the separator, and make sure those are as far apart as I can so that I get this clean separation down the middle. That's going to be our objective. Now let's see how to do it. First thing first, we have to parameterize the line. We've seen lots of different parameterizations of the line. We're going to revert back to the parameterization that we use for total least squares, which is we're going to parameterize the line with a little vector that is perpendicular to the line. This is the classification surface of which the margin is on either side. So in particular, if my axes are x1 and x2, then points on the line satisfy w1 x1 plus w2 x2 plus b is equal to 0. Now, I've drawn this line going through the through the origin, so that b is 0, of course. But I could take that line and I can move it up and I can move it down, and that b will move positive to negative corresponding to whether I shift up or down. Any point on this line will satisfy this equation. Why? Because the dot product between w and x, the parameterization of the line, and any point on the line should be equal to 0. And then, of course, the b is just what pushes the line up or down. Okay, good. That's the parameterization we are going to use for our separation. Now, let me remind you that this dot product right here, w, which of course are the parameters of the line, and x, which is the data, the dot product, if these two vectors are unit length, is equal to the cosine of the angle between two vectors. So take any two vectors that are unit length and compute the dot product, and that is equal to the cosine. Why am I writing this? Well, sure, it's fine to think about points on the line, but what about points that are on this side of the line or this side of the line? What does this dot product tell me about them? Well, let's see. If the angle between the vector w and any point up here is greater than 0, that means it is bounded between minus 90 and 90. So when the dot product of the data and the model is greater than 0, then it must be on this side of the line. Good. And you can see that just from the cosine over here. This space is from minus 90 to 90, corresponds to a positive dot product. On the other hand, if the point is on the other side, then the dot product with w is going to be negative. Okay, so why did I want to draw that? Because this is what a two-class classifier is. We are going to draw this line, trying to figure out by maximizing the margin, and I want to know what's below and what's above that line. And the sign of this thing right here tells me what it is. And by the way, notice I've drawn this line at the origin, but it doesn't matter because I have that b term over here, and that b term will allow me to move the line anywhere in this space that I want, so it doesn't matter. All right, so now let's go back to see how we can use this for classification. I've got class 1 blue, class 2 red. Now, if the dot product between my model w, what is w? It is the vector that is normal to the line, because I'm still assuming a linear separator. If the dot product between the line and any data point plus the offset b, I've again drawn at the origin, but it doesn't matter, is greater than 0, well then I'm in class 1. Let's call the label y sub I associated with x sub I equal to 1. And if the dot product of the model w with the data point x sub I plus b is less than 0, well then I'm in the other class, let's call that negative 1. All right, so now I have a parameterization of my space here. I haven't told you how to figure out what w is. I haven't actually defined the margins yet. I'm just specifying the objective, following that same pattern as before. What's the model? What's the objective? And then we'll worry about how to optimize it. Okay, now, so I sort of want to do two things here. When I'm in class 1, y is equal to 1, I want the dot product of w and x plus the offset b to be greater than 0, and I want it to be negative otherwise. Now, I'd like to be able to bundle all that up into one thing so I can maximize or minimize it. And so let's look at this. Let's define y sub I to be the sign of this dot product. Well, let's see what we're doing here. So what is the dot product? W times x plus b. That's what I've been showing you over here. So we've already agreed when that is greater than 0, I'm in class 1. And when it is less than 0, I'm in class negative 1. So we can just define y sub I to be the sign of that, and then y is the class label. And now I can have a single optimization that looks like this. I'm going to I want to find the w that says that yi, class label 1 or negative 1, because y is defined to be the sign, the product of that label times wx plus b, which is what we've just been talking about, should always be greater than 1 no matter what. Let's see why that is. Well, if y is equal to 1 and this is equal to 1, well then the product is greater than or equal to 1, or is positive rather than it's greater than 1. If this is negative 1 and this is negative, well then it's greater than or equal to 1. So all I've done is I said this class label is 1, negative 1, and this term here, which is my classifier, is either going to be positive or negative. I'm going to take the product of the two, and it should be always greater than 1 no matter what data point I'm looking at. So that's nice because now I have a very simple objective that I want to maximize or respect no matter what the data point is. Okay, now, I haven't actually done much of anything other than specify an objective. I don't know how to solve for it. I don't know how to maximize that margin, but I have now an objective. And now what we can do is start thinking about how do we satisfy that objective, the product of the class label times w, x plus b should always be greater than or equal to 1. That's my objective. And now the question is how do we satisfy that and maximize the margin for the linearly separable SVM? And of course, that's what's about to happen next.